Yeah, so let's learn scattering of light. So whenever light is coming from one medium to the other or wanting to go into the other medium, things are happening like reflection is happening, refraction is happening, dispersion is happening. So there's another thing which happens which is called scattering of light. Okay, so first this thing was revealed or studied by Tyndall. Have you heard the name Tyndall? Tyndall effect?
Yes, sir.
Yeah, I mean this guy was he has done a lot of things. Okay, he has a lot of papers. The greenhouse effect is he has studied that initially. So Tyndall effect actually could not really come up with the explanation why sky is blue, and that is why we are doing the lesson, because sky is blue is what is there in the course. Okay. And but it gave a lot of hints to other people of how things are happening. What Tyndall was doing is basically to figure out that air is having how much of, say, suspended particles, aerosols, how dirty the air is, how smoky the air is. How would you know? If you want to find out how smoky the air is, how would you know? What is there to figure out that there are things in air? What better than light, right? Right? So he's flooding the things with light and trying to observe some things. Get the point? And he did come up with some observations. Like initially it is becoming, I mean he's seeing some bluish tinge here, and the right light which is coming out is reddish. So we'll be doing Tyndall effect in a bit more detail, but just to give you an idea of but it fell short of explaining why the sky is blue, because in sky we are really dealing with very very tiny particles. What are those particles of sky, guys? Sky particles. What can that be? What do you mean by sky particles? That's air itself, no? The molecules of air, like N2O2, bit of carbon dioxide, right? Right? So, yeah, but others got a hint of what is happening and how it is happening. So, this guy, Lord, in fact, really, so he gave a precise mathematical model which explains why sky is blue. Okay, so this is a photo that has been taken from a height of roughly 20 kilometers, and it's an actual photo. You're seeing that the whole sky is seemingly blue, right? Right? So this model what he gave really gave, it works only on very tiny size particles, very very tiny size particles which are lesser than 40 nanometers. Get the point? Get the point? Any idea of how big a molecule is? Say O2 molecule, N2 molecule. Any idea? The air molecules. Any idea? Roughly 300 picometers. Okay? 300 picometers, meaning to say how many nanometers? How many nanometers? 300 by 1000. Right, people? Right, people? So that's the size of molecules, and he came up with a model which is basically your scattering is more effective if the wavelength is low. Okay, which is true in the Tyndall case also, but I'll go into the details after what is there in the main course. Okay, what is there in the main course, I'll do that, and then in extra class or a bit of more detail I'll explain you what is the difference in what Tyndall said, or Tyndall figured out till which level, and what Rayleigh did. Okay, so this is valid only for particles which are very very small, less than say 40 nanometers, right? And me came up with a mathematical model. Obviously later you see when he what is his duration of lifespan. So he came up with a mathematical model which explains your scattering in Tyndall effect also. So this is for larger particles. Okay, so larger particles which are in the range of the wavelength of light. So if I'm talking about say visible light, then visible light is what? Roughly 400 nanometers to what? 800 nanometers, right? Right. So there is no upper limit to the size of the particles over here. For smaller particles, the mathematical model what uh, me gave will not be of any consequence, and similarly for the mathematical model given by Rayleigh, the bigger particles is not going to demonstrate any scattering. Okay, it's not like you cannot apply, you can apply, but it is not going to give you much of scattering. Is that clear? So we don't have to get into the details of the mathematical model, and obviously the explanations of Rayleigh and me are different, but what I'll try to do is I'll give you a rather simplified explanation, okay, which may not be completely and totally correct. I am admitting that what I'm going to say is not totally correct, but good enough for what is being asked in school level, and good enough to explain a lot of phenomena which is happening around us due to scattering. Is that clear, guys? So don't catch hold of me that you said this. I am saying that what I'm saying is not totally right. Okay, so the totally right part may come in episode 2 of this. Okay, is that clear? So let me again draw say a white light is coming. ये है तुम्हारा say white light. So it is in fact made up of all kinds of wavelengths, from very tiny ones like X-rays and all to the very long ones like radio waves and all, but I am interested in what I can see. So let us take the blue end, and those waves are there, right? What are these? Electromagnetic waves. Your scattering is best explained as a wave phenomena. Okay, and say these are your red wavelengths, which is almost double the size. It may not be coming exactly double, so don't worry. Okay, just wanting to show that one wavelength is larger than the other, right? Now in my way of explaining it, let me just tell you that if larger wavelengths are there, if the wavelength is large, say wavelength is so much, it is going to miss out on striking the particles which come in the way. Are you understanding? It's not like light is going like this, it is not like that, but I'm representing like this. Okay, if you can see my hand, it is like the disturbances are growing and becoming lower and then higher and lower and higher and lower. Okay, so that is how it is traveling, but I'll just represent it like a wave. Your router antenna is giving out a wave, which is my router antenna is giving out a wave which is coming to my laptop, and I'm transmitting this, right? So that wave is also a light wave. It is coming right through the walls. Why it is coming right through the walls? Because the wavelength must be larger than the width of the wall. We generally study 1/4 of the wavelength, but that's the reason why it is coming right through the wall, right? If you swallow a mobile phone and I call you, it is still going to ring. Why? Because the electromagnetic waves or light which is going to the antennas of the mobile phone is still going through the skin of yours, right? Of your tummy. Are you getting the point? Are you getting the point? So when you want to switch on, or when you want to say open the doors of your car, you can use the remote key right through the walls. It opens. Why? It is giving radio waves which are much larger, right? So the car can see your key. Are you understanding? The car can see your key. While suppose you are in the car, you can't see that key. The key is being operated by somebody else across the wall. You can't see the key. Why? Why?
Because the wavelength of visible light is smaller than the
Yeah, because the key is giving out whatever wavelength the key is giving out, that is going through the wall. Car is seeing it, right? The key is giving out visible light which is not going through the wall. It is getting reflected from the wall, right? And you can't see the key, right? Is that clear? Is that clear?
Yes.
But the receiver of the car is able to receive the radio waves from the key, which is coming through the wall, right? So we are trying to use that concept over here, which I have already said is not like the true use of it, but still. So let me know if I have a particle, if I have a particle, okay, which is say fairly tiny, and I have a wave coming like this. I have another wave coming, say like this. What do you think, which wave is likely to hit the particle? Both may hit, both may miss. What do you think?
The blue one.
Yeah, so just to make it like excessively small and all, if a wave is coming like this, it is likely to hit, right? And if the wave is coming like this, it is likely to miss, right guys? Right guys? Right guys?
Yes, sir.
So this phenomena of scattering is particularly being studied if the particle is very minute. Okay, so what is scattering? We'll say scattering is, if you want to write, you can write bouncing off. So we'll use the word bouncing off over here of light. Bouncing off of light. Okay, what is bouncing off of light? Have you heard of it in other phenomena? Like bouncing off of light is what? Actually, one of the things what you have done earlier.
So
It is
reflection.
reflection, right? Straight away reflection, right? But I don't want to use the word reflection because in scattering it is not actually reflecting. It is not actually bouncing off also. It is actually absorbing and re-emitting. Okay, so we don't want to get into that. Okay, that's the actual thing what is happening in scattering. It is going to absorb and re-emit. Okay, why does it absorb? Because after all, light is electromagnetic waves. The particles which I am talking about is made up of electrons, right? So those electrons will get influenced by the electromagnetic waves. They will start wiggling, they will start vibrating, right? Right? And those vibrating particles in fact will generate their own waves, right? And that is how scattering is actually explained. So we are not going to that minute detail right now. So we'll use a very loose word over here, bouncing off of light. Is that clear? Is that clear? Holds
Yes.
good for say your next 2-3 years of studies. Okay, is that clear? Not 2-3, you are in ninth, right? So 2 years of study. Bouncing off of light by what? Minute particles, minute or fine. So that's the big difference when we are talking about scattering or reflection. Reflection is from massive things, right? Here we are talking about particles which is comparable to the wavelength or even smaller than the wavelength, right? As I said, wavelength of this blue light is what? Say 400 nanometers, and size of the air molecule is what? Say 400 picometers, right? 1000 times less, right? Are you understanding? Are you understanding? So this is a phenomena where your bouncing is happening or your scattering is happening by very fine particles. Is that clear? Is that clear? So I hope you have understood that if a large wavelength light is coming versus a small wavelength light is coming. This is a large wavelength light versus a small wavelength light is coming, then the likelihood of hitting will be more with what? The small wavelength light. Okay, so in this part of the chapter, you are going to concentrate on words like probability, likelihood, or chances. Yeah, probability, chances, likelihood. Is that clear? Is that clear? So, lower wavelengths will have higher chances of hitting the particles, right? Right? And mind you, the actual particle is like 1000 the size of the wavelength. So, this wavelength is around this size, right? 1000 will be really a dot, right? Right? So, mostly both are going to miss it. But if it at all anything hits, which one will be like higher chances of hitting? The blue light, right?
Smaller wavelength.
Yeah, the smaller wavelength one, right? Get the point? So this is a rough explanation of what is happening, and it is a fact that scattering will happen more for lower wavelength light. Okay, so Rayleigh's or Tyndall effect both correspond to your scattering is proportional to 1 by lambda power 4. Lower the wavelength, more is the scattering of that light. Is that clear? Is that clear?
Yes, sir.
Is that clear? So is what is scattering is clear, right? Shall I ask you a question on this? So suppose I have a particle which is this big in front of these two wavelengths, which is going to get scattered, which is going to get scattered.
Can you repeat the question?
If I have a particle this big, instead of the dot particle, I have a particle this big, which is going to get scattered?
So
The
both.
blue one or the red one?
Both of them.
Both of them are going to get scattered, right? Right?
Yes.
So larger particles and still like in the range of being called as particles, okay? But say more than say 900 nanometers in size. Mostly both are going to get scattered, right? Why? Because it is larger than the largest wavelength over here also, right? Right? So this me scattering is going to deal with that. Okay, it deals with all large particles. It comes to a level where it is more of a reflection rather than scattering, which is the predominant thing. So we don't even study that. Is that clear? Is that clear? Like scattering by say a piece of chalk or something. No, we won't be talking of that, right? But scattering by dust we'll be talking. Is that clear? Where we talk of scattering from really minute particles like molecules to really large suspensions like your dust particles. Is that clear? Is that clear? But all those scatterings are explained mathematically by different models. Same model is not explaining everything. And we are not getting into the model, we are just getting into a rough idea of what it is. ठीक है? ठीक है? Okay. So I showed you that picture, no? I'll show you one more picture. But I'll show it later. Okay, pictures later. Now the main thing which is there in your course and why we are discussing scattering is your reasoning of why sky is blue. Okay. Now you would have understood, you would have guessed, I guess, but we'll do it anyhow. Say this is sun, way away, and that's your earth down there. Okay. Here is Mother Earth. 1 second, guys. Sorry. Is that clear? Is that clear? So, excuse me. What is coming from the sun? Which colored light? If I talk in terms of colors, huh?
Light
Yeah, white light is coming from the sun, right?
Yes, sir.
White is a mixture of everything. So it's going in all directions, but we are interested in what is coming to my eyes. Suppose I am here. What is coming to my eyes is what I'm interested in, right? Right? Light obviously from sun is going in all directions, right? Right? So if you are in outer space, like somebody described us, no, what is outer space? Officially it is more than 100 kilometers, right? Above Earth. You go beyond that, it is outer space, right? So from outer space, if you look at sun, it is all white, dazzling white. But from Earth, when you see, it is not dazzling white, and that is the reason what we are going to do right now. So I've just drawn a layer of atmosphere over here. So that's your atmosphere, okay? And that atmosphere is having how much of a height, guys? Can you tell me? Like it extends till what height? Atmosphere? Yes, people?
10,000 kilometers.
10.
Yeah, it really extends like till 10,000 kilometers. 1 second, man. Yeah, so the atmosphere, like you can keep on taking for, as you said, 10,000 kilometer and all. But Mount Everest, you know, no? How much is that Mount Everest? Around 9 kilometers,
8.6.
right? So
Yes.
that itself, you have thin air, difficulty in breathing. That's say 10 kilometers. Then 100 kilometers is your space limit officially, right? So after that, it is really thin, right? So if I take 10,000, no, the radius of Earth itself is 6,400. If I take 10,000, I'll have to draw the atmosphere over there till there, okay? So very thin, thin, thin. Suppose it gets denser, denser, denser around this range. Is that okay? Just a representation, okay?
Yes, sir.
Okay. So maybe 100 kilometers or something. Now, once the light enters, light is coming with all its colors, right? Vibgyor, right? Of which whenever I'm talking of blue, I'm talking of the blue end. Is that clear? Is that clear? Is that clear? Vibgyor. Violet is really dim for us. For human beings, violet is really dim, right? So if I have equal intensity of violet, indigo, blue, it will all look bluish only. Get the point? Get the point? This is how it becomes dimmer and dimmer this side and dimmer that side. Get the point? Okay? Yellow is the brightest for us. Violet end and red end is dim. So when I say blue, just think of violet, blue, all those mixture I'm talking about, and we are perceiving it as more of a blue color. Is that clear? Is that clear? So when that blue and red light is going to enter over here and is going to pass kilometers and kilometers of air, kilometers and kilometers of air, like in front of you, white light is there. It's coming from sun, white light is there. It is passing through the air particles. But is it like striking those air particles? Maybe in a million, one is getting struck, right? In the sample space in front of you. Are you getting the point?
Yes, sir.
So, if a million red is coming and a million blue is coming, one blue is lost because it gets stuck. You'll still have the perception of it being totally white, right? Get the point? That is what is happening in front of you. Very few particles of air or very few molecules of air is there. So the chances of blue or red hitting is very low. So the whole of blue and red, the whole of blue or red simply passes. Is that clear? Is that clear? But if I am talking about this region as kilometers and kilometers of air, kilometers and kilometers of air, then what is going to happen? Then what is going to happen? Then what is going to happen? The amount of blue getting scattered would be high or not? The chances will be even higher or not, right? So that time the blue which is coming out, maybe 20% is lost, only 80% is coming, right? Right? And the red, just to say 1 or 2% is lost, 98% is coming out, right? Is that clear? Is that clear? Is that clear, guys?
Yes.
Yes, sir.
Any doubt you ask? Any doubt? Yes, Anirudh.
So like what happens to the other colors like green and orange and those ones?
Yeah, everything. I'm talking of everything. I'm just talking of the extreme ends. So this is, say this is yellow, bigger wavelength than blue, but smaller wavelength than red. So what is going to happen to that?
Sir, around
That
90%.
will also get scattered, okay, but highest scattering will be with blue, right? Right? And they have studied that it is proportional to 1 by lambda power 4, meaning to say what? It really becomes high as the wavelength becomes small. Is that clear? It's not like a gradual change. Are you understanding? So I
Yes,
can't
sir.
do a average over here कि इसके बीच का होगा. Blue is really highly scattered, and as the wavelength grows higher, it is really less scattered. Is that clear? Is that clear? So that's the math
Yes.
what they have given, and if you want to see the mathematical equation, we can show you, but not in this class. Okay, next one we'll do that. Is that clear? Is that clear?
Yes, sir.
So now, what is the story so far? Light is coming, light is entering the atmosphere, and slowly, the blue light is getting scattered as it comes lower and lower and lower, and the red light gets scattered very less, right? So what comes to us is the white light which is deprived of the blue end a bit, right? Is that clear? If the white light which is coming to us is deprived of the blue end a bit, what is the color we will see? Like this is the light which is coming from the sun for us, right? So we'll think that the sun is of that color whatever we see. Is that clear? So what are we going to see?
Or a slightly yellowish light.
Yeah, slightly yellowish, absolutely right. Okay, because it is not dazzling white now. Why? Because it was not a perfect mixture of all the colors, right? From the perfect mixture, I have reduced this, reduced. It's not gone totally, it is reduced. Reduced. Is that clear? Is that clear?
Yes, sir.
Yes, sir.
If I say this explanation is wrong, then you would kill me, no? But we'll go with this explanation, okay? What actually happens in Rayleigh scattering is the scattering happens only on the top parts, okay? Where the air is rare, no, there it happens. And at the bottom part, there are really high molecules of air. Density of air has increased, right? So you would imagine higher scattering, right? Right?
Yes, sir.
Surprisingly lower scattering happens at that range, okay? So we'll have to actually go into the absorption and re-emission thing, okay? And little bit of superposition of waves, but we don't want to do that. So for now, this is a Tyndall kind of thing what I'm telling you, okay? What I'm saying is the Tyndall kind of thing. The Tyndall was the first guy to start everything. So I hope you understand, like we are not on the absolute right track when I am explaining like this, but it is an okayish kind of explanation. Is that okay? This is the explanation what you have to write in the school exam which it comes. If you write any other thing, you'll lose marks. Is that clear? That's a sad story. Is that clear?
Yes, sir.
Is that clear? Okay, if it is clear, then tell me why sky is blue then? Why sky blue? Why sky blue?
So also the blue light gets scattered, which is why we see blue.
Yeah. So we see anything. Why? Because if I'm seeing the color of somebody's shirt, why am I seeing that? Because that shirt is reflecting that color, right? 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 So the super cool thing happening over here is these molecules are reflecting the blue color, no? So what we are seeing is actually the molecules. We can't even imagine, but we are seeing those. Are you understanding? We are actually seeing the molecules. Can you see the molecules in front of you? Absolutely no. But why are you able to see the molecules of the sky? Why are you able to see like an impression? Because there are kilometers and kilometers of it, right? Right? ये कुछ देगा वो कुछ देगा. If a single light was coming, it is so bleak, it is so less, you can't see it. But if it is coming like one behind the other, one behind the other, many molecules, then you actually get an impression, right?
So, sir, if red had a smaller wavelength than blue, we would have had a red sky.
Absolutely, man. Absolutely. Okay? Get the point? So is it clear why sky is blue? So how are you going to write in the exams? If you have to write in the exam, how are you going to write it? Yeah, you have to write few things. White light comes from sun, which is a perfect mixture of all the colors. Okay, lower wavelength and higher wavelength, right? The probability of blue light getting scattered, so you note it down, okay, is higher because of its lower wavelength. Because of what? Lower wavelength. And one more thing you add over here is getting scattered by you have to add something over here. Scattered by minute or fine particles of air, which are the molecules of air. Fine particles of air, in bracket molecules. Are you getting the point? So if you use the word probability, getting scattered by fine particles, probability, and why is the probability higher? Because the wavelength is lower, right? Lower wavelength. If you use these three in any which way you form the sentence, you are going to get the marks. Is that clear? Is that clear? So the crux is, if the wavelength is shorter, then the probability of scattering is higher. Blue being the shorter wavelength, it is getting scattered the most. Is that clear?
Yes.
Is that clear? So whatever the molecules are giving out the light, okay, it's actually emitting the light, okay, instead of bouncing off, it is giving the light, is what we are seeing. Okay, so you don't have to write the giving out or emitting, you may just write scattering. Okay, so the molecules are scattering blue light, hence we are seeing the sky as blue. Is that clear, guys? Is that clear? So same explanation goes for why sun is slightly yellowish. So you'll write all the same thing, and towards the end what will you write? Everything same, but towards the end what will you write? That since blue is scattered, what comes to us is white light deprived of the blue end, right? Slightly deprived of the blue end, hence it is yellowish. Get the point? Is that clear? Is that clear? Is that clear?
Yes, sir.
Okay, can I ask you something like a very cheap question, or I'll ask you a bit later? Okay, say we are talking of dusk or dawn. We are talking of the time when the sun sets or when the sun is rising. Say here is the sun, and again the light is coming to you. A lot of phenomena are happening. One is there is atmospheric refraction, but I'll just not consider it. Shall I draw a straight line? It is not going to come straight. As soon as it comes to the atmosphere, it starts refracting, right? We know that, right? But for this part of the chapter, I don't even have to emphasize on that. For this particular phenomena, what I'm going to talk about next. So the light comes and light is reaching to your eye. So you are able to see the sun, right? You are able to see something because light reaches, right, from that object to you, whether it is its own light or it is reflecting or whatever. Now my question to you is, what do you think? The sun will be same yellowish kind or more?
Sir, it'll take a shade of red because the
Okay,
blue.
okay. 1 second. Tell me a name. Somebody tell me a name and tell me why it will be more of red. Who said it will be more of red right now?
Sir Aditya.
Aditya. Okay. Somebody just tell me why is right or wrong. Somebody else. Tell me a name. Is he right? More of red. I mean, every morning or every evening you can watch it. Have you not watched?
Sir, can I prove my statement?
Let me see somebody else. Nobody.
Okay, so is it because more of the red light comes straight and the more of the blue light gets scattered in all directions? So you see it as red because it comes straight to your eyes.
No, whatever comes straight or bent or whatever, if something comes to my eye, I am able to see that. Okay, this straight to the eye thing is, I'm not buying that thing. Rest what you said is okayish. This is suppose an object. This is an object, okay, and say 1 second, excuse me. Say you are here, so I'm just making your eye. ठीक है ना? Is that clear? That's your eye.
Yes, sir.
If a light is going like this and somehow comes to your eye after say reflection, refraction, whatever it does, you see the object. You see as if the object was in front of you. You see the object. You see object if the light from the object comes to you. Okay. If the object, light of the object, or if the light comes straight to you, this is the object and the light comes straight to you, then your perception of where the object is correct. If it is bending and coming, then your eye may be thinking that the object is somewhere here because your brain says that light comes straight to you, right? So your perception of the object being where may be wrong, but you see the object in both cases. Get the point? Like a drastic example of this is, say, reflection from mirror. Idhar gaya, idhar aaya, right? You are able to see the thing or not in the mirror. If the mirror is very clear, it is like as if you don't even know you are seeing the reflection. Your perception is, okay, the object might be here somewhere, right? Right, guys? So if the light reaches your eye from the object, whichever way, by bending, by reflecting, or whatever, okay. So that part, it comes straight part, I don't buy that, okay, and it is actually bending and coming. The rest what he said is okay. So somebody else, why the sun is red?
Sir, can I?
Name.
Sir Aditya.
Okay, tell me.
So the light has to travel further, so there's more scattering of the blue light.
So what do you mean by further, here to there?
No, sir. The sun is in a slanting position from where you are seeing. So there's more distance the light travels.
From where to where? Distance from where to where? That's not a very good scientific sentence. Where to where?
From the atmosphere, like what actually matters is from the atmosphere to where you are standing because it's slanting.
Yeah, so you have to say that within the atmosphere it is traveling for a longer distance. Get the point? Because there is one very wrong answer which is taking the round, like people write. If the board teacher is little aware and little vigilant, you are going to lose marks. Okay. So guys, he is absolutely right. In this atmosphere, can you see that this length is much larger than that length? Can you see that, people? if we had assumed this height of atmosphere roughly to be say 100 kilometers, roughly, okay, like if I'm talking of that as 100 kilometers, this is much larger than 100, looks like double, more than double, right guys? Right people?
Yes, sir.
So what kind of yellowish the sun looks like would be to a person who is like flying high over here, right? Then for that amount of atmosphere, the blue light would have got a equal chance of getting scattered, right? So if you give so much of extra atmosphere, what is going to happen?
More scattering
More of blue light will get scattered or not, right? So what is coming from sun, equal amount of blue, red, green, yellow, everything, right? Of which after scattering, what is happening is, what is reaching your eye is really tiny amount of blue, if at all, and still a large amount of red, right? Right? So a sun color looks like this. Is that clear? Is that clear? And the sky would have been, is looking more of what? Violet, blue, really deep, right? Is that clear? Is that clear?
Yes, sir.
So
Yes, sir.
what's the big wrong explanation goes that sun is farther from earth. That I hope you will never write. Even if people are willing to give you marks for that, don't write. Okay, that's almost a crime. Let me just make sun and make earth. So if this is your sun, right? If I have to fit the frame, I'll just make my earth over here somewhere. That's my tiny earth, right? Right? So what the explanation says sometimes is light is, sun is farther in the evening, hence the light has to travel more. Is that clear? Is that what is happening? How is evening and morning happening?
No, sir.
It is just rotating, right? The earth is just rotating, right?
Yes, sir.
On its axis. So if it rotates a bit and it is like 90 degrees off from the initial position, is the distance between the sun and earth changed? Not at all, right guys? Not at all, right? So don't write that the distance is changing. Whatever starts happening, the phenomena starts happening when it starts entering the atmosphere. So you'll have to make a diagram as the one made earlier. Where is the diagram gone? Like this, and you have to emphasize on this length. So you have to very clearly state that the amount of light which is going through the atmosphere, the length through which the light has to go in the atmosphere is longer in the evening time than in the noon time. Is that clear? Is that clear?
Yes, sir.
The sun would be really red. Sun would be really red. So that's it. That's about what how you explain the phenomena of scattering. So let me ask you a few more things on this. Like extending this, if they ask you why red lights are red. By the way, I've just told you in the previous class that red light is the coolest for human being, and blue light is not for human being. Red light is the coolest in the visible range, and blue is the hottest. More is the frequency, more dangerous is the light. But why is red used as in red lights? That's a very common question which comes in your CBSC as explanation based on these things. Anybody? Anybody?
So because it will scatter less.
Yeah, it will scatter less. So even from a distance, absolutely right. Even from a distance, from far off distance, it is going to reach your eyes. That sometimes that matters more than what is the intensity and all. Okay? If it is long distance away and it is blue light, okay, then maybe blue light is getting scattered and becomes hazy, and it is not reaching that strongly. Is that clear? Is that clear? So if the question is asked, you'll have to just write this. There is no other option. Okay. It can very well be that in the human psychology, red is danger and danger is stop and all. But if they are asking in this, you'll have to write that. Okay. Really, if the light was blue also, the distance at which these red lights are, we can easily see it. Right, guys? Right, guys? Yellow things are generally made because it is the brightest. You see the topic over here is written in yellow, scattering of light. That's the brightest. Why? Because it is right in the middle of the range what human perceives. So I guess it is clear. I guess it is clear, right? Let me just emphasize one more thing over here. Or why is cloud white? Why is cloud white? And what do you think is the color of the cloud in the evening? Cloud color. A bit on that. Anybody? Let's discuss a bit on this. Cloud color. Anybody?
So, like, does the cloud disperse all colors, but there's no real change?
Yeah, don't say disperse, say scatter, right? It is scattering all colors. Why is it scattering all colors?
So it has water in it, so water scattering by water is much more.
Yeah, suspended water droplets or the scattering particles are much larger, so all the wavelengths are getting scattered, right? Whatever is reaching is getting scattered, right? Are you understanding? So if blue is reaching, blue is getting scattered. If red is reaching, red is getting scattered. So if all of them are getting scattered and you were interested in the in between one, the green one, okay, if everything is getting scattered, then this mixture is what? White, right?
Yes.
Then comes a question like, why is evening cloud red then? Why is evening cloud red? So while you answer, I just make a tiny cloud for myself. We have talked about the morning cloud. Oh, I'll not make it. If I make it, then maybe it's a hint. Why is evening cloud red then? Why is the evening cloud red? Tell me your name and then you answer. See, cloud or fog or mist are having suspended water particles. Okay? Not water vapor. You have tiny globules of water itself, which is much larger than the wavelengths of the visible light. Are you understanding?
Yes, sir.
Those condensed water particles are there, and the whole particle, since it is larger than all the wavelengths are going to get scattered, right? So it is like you can say that agar if it was not a mist, say it was actually a big thing, I would have called it as reflection straight away. But in reflection, what happens? What is the big difference between reflection and scattering? Reflection will follow the laws of reflection. The angles are known, right? In scattering, what happens? There is absorption and re-emission where angles can be random. Get the point? Get the point? So it is not like they will not be reflecting. They will be reflecting. And they are scattering also. As I told you, there is no upper limit to scattering. So till where the reflecting effect is more or scattering effect is more is all debatable till which size of particle we are talking about. So we'll just go on the size of particle a bit when I come to Tyndall effect after this. But any which way you explain, the answer would be same. Get the point? Because in fact this scattering also I was explaining as tiny reflections only, no, bouncing off, right? Right? So you explain any which way, your answer is going to be same. So try it. Excuse me. Why is cloud reddish in the evening? You would have noticed, no, reddish cloud in the evening? Yes or no?
No, sir.
Ayyoppa.
Yes, sir.
Yes, sir.
Today evening you notice it, okay? Bangalore is always cloudy. You just notice it, okay? If you are at all able to see the sky, you won't be able to see nowadays. But if you are able to see the sky will be like deep purple, blue, dark blue. Get the point? Dark purple meaning to say. And the cloud would be red. Okay. I'll next ask you, the whole sky looks like red. That is why, that is also I'm going to ask you. That's how you are perceiving the sky sometimes. That would be my next question. Right now you just tell me why the clouds are reddish in the evening, near the dusk or even in the dawn time.
The same explanation of why the sun appears to be reddish in the evening.
Yeah, same only. Just put it in the right words and tell me.
Sir, Aditya.
Yeah, somebody else. Fast, fast, fast. Yeah, tell me.
So is it because in the evening, like when the Earth, the distance between the cloud and the rays that enter through the atmosphere, like it has to travel more distance, so the blue light gets scattered more, but then there's still a lot of red light left, and the red light gets scattered by the cloud as it reaches the cloud.
Yeah, okay. In some other words, anybody? Okay, now let me draw the diagram. In the morning time, it was white.
Aditya.
Your cloud is somewhere. Yeah, Aditya, tell me.
Uh, so, so we already know that the blue light gets scattered when it enters the atmosphere. So light without the blue, light minus the blue part reaches the clouds, and so the clouds scatter all colors equally. So red light remains in the cloud.
Absolutely right. Cloud height, right? Guys, what is the height of the cloud? The really low clouds are from ground level. You know that sometimes the cloud is going to come on the ground. If you are living on hills, you would have, I mean, gone to hills, you would know, right? Little higher. So, clouds are as low as say 1 kilometer, 2 kilometers. And the highest, the thin clouds and all, the highest clouds they say is like 20 kilometers. Get the point? When you go to aeroplanes, and you would have noticed, no, various layers of cloud. The lower one you cross, and then there is a higher one, right? Right?
Yes, sir.
The middle one, the higher one. So 1 kilometer, 2 kilometers, highest being 20 kilometers, and here we are talking about a lot of distance, right, of atmosphere, right? So the clouds which we are seeing are very near, 2 kilometers, 3 kilometers, 20 kilometers at the max. Okay, 4 5 kilometers cloud is what we are seeing. So by that time what has happened? Blue has all scattered off, right? And what is remaining of the light is what? The red light, right? So if the red light is falling on the cloud, it is going to reflect the red light, right, guys? Right?
Yes, sir.
So as somebody said, the color of the cloud is color of the sun. Whatever light is coming to us is the light which is coming to the cloud, because cloud is really near to us. Is that clear, guys? So cloud reflects the color of the sun, whichever color you are seeing at that time. Is that clear?
Yes, sir.
Okay. What else is asked in scattering? Okay, there is another big confusion or wrong answer. I'll do that a bit later. Let me just extend this to Tyndall effect. You guys have any other question to ask over here?